Section: Introduction. In recent years, there's been a surge of interest in training models that can generate images from text and vice versa. These models have shown remarkable capabilities, such as creating realistic images from text prompts and providing accurate descriptions of images. However, training these models to perform exceptionally well requires massive datasets of paired image text samples, which are costly to collect and often of low quality. Meanwhile, large datasets of unimodal images or texts are left unused in this training process. This leads us to ask, can we use unpaired image and text data to improve the training of these models? The main challenge with using unpaired data is the lack of supervision. To address this, we propose a new training approach called ITIT. This method uses a cycle consistency loss between cycle-generated images, texts, and their original inputs to supervise image-only and text-only data. ITIT uses a small set of paired image-text data to achieve reasonable performance in generating text from images and vice versa. At the same time, for unpaired image or text data, ITIT generates corresponding text or image counterparts and uses them as inputs to reconstruct the original input. This is known as a full cycle loss. We consider two types of full cycles: T2I2T, which starts with an unpaired text sample, and I2T2I, which starts with an unpaired image sample. These cycles allow us to use both unpaired image and text data to provide informative supervision signals for training. To enable this cycle training, we first unify image to text and text to image generation in the same framework, using a bidirectional image-text encoder and separate image and text decoders. For image-to-text generation, we use an autoregressive text decoder, while for text-to-image generation, we use a non-autoregressive parallel image decoder, which is significantly faster than autoregressive image decoders. One technical challenge we faced was that the processes for generating text-to-image and image-to-text typically involve multiple forward steps of the model. Back-propagating the gradient through all these steps requires significant memory and computation. To solve this, we back-propagate the gradient through only one step of the decoding process for each cycle. This greatly reduces the computational overhead of cycle training, making it feasible to apply in large model settings. We tested ITIT on standard benchmarks for image-to-text and text-to-image generation. We found that by using unpaired data and cycle consistency, ITIT achieves performance levels similar to a non-cycle baseline, but with much less paired data. ITIT also scales similarly with unpaired data as the baseline does with equivalent amounts of paired data, while being much more robust to low data quality. In summary, our contributions are as follows. 1. We introduce a framework that unifies text-to-image and image-to-text generation, and propose ITIT, a novel technique that enforces consistency between cycle-generated images, text, and their corresponding originals. This approach allows the training of image-to-text and text-to-image models using unpaired image and text data. 2. We comprehensively evaluate the proposed ITIT framework and the image-text cycle consistency method, and demonstrate that they significantly enhance model performance. 3. We show that ITIT can achieve performance on par with state-of-the-art methods on common text-to-image and image-to-text benchmarks with much less paired data. 4. When scaling up training data to improve model efficacy, we show that we can add only unpaired examples using our framework and achieve similar performance as scaled-up paired data, without the downsides of significant manual effort and poor pairing quality. In the literature review, we discuss various works that explore generating textual descriptions from input images, either training the network with generative loss alone or combining it with contrastive learning. We also discuss recent works that focus on two primary paradigms: diffusion-based models and token-based methods. We also mention works that have tried to use unpaired image and text to train image captioning models in an unsupervised way. However, these applications are limited to pre-training and do not encompass the entire generative vision language training procedure, thus providing only incremental improvements. The concept of cycle consistency has previously been used to provide regularization and/or compensate for a lack of annotated data. However, none of the previous works has explored the potential of cycle consistency in generative vision language training using unpaired data. Our novel approach diverges from preceding vision language models that heavily rely on either a large corpus of paired image text data, or fine-tuning methods that target only text or image encoder decoders separately. For the first time, our method facilitates the utilization of unpaired image and text data during generative vision language training. This innovation significantly reduces the dependency on paired image text samples during the training process, which empowers the expansion of generative vision language training to nearly boundless text-only and image-only datasets. Section Summary. Image-text multimodal training has gained attention, but collecting large paired datasets is costly and raises quality concerns. To address this, we propose ITIT, a training paradigm that uses cycle consistency losses between cycle-generated images, texts, and their originals to provide supervision for image-only and text-only data. ITIT achieves performance similar to a non-cycle baseline with up to 100x less paired data and is more robust to low data quality. Section Method. We've developed a novel framework, ITIT, which is the first of its kind to allow for generative vision language training on unpaired image-only and text-only data. This framework is built on a simple yet effective architecture that includes a unified image-text encoder and two separate decoders for images and text. This design allows for both text-to-image and image-to-text generation within the same framework, leading to the possibility of text-image-text, T2I2T, and image-text-image, I2T2I, cyclic losses. Let's delve into the details of each component of our ITIT architecture and the cycle consistency training paradigm. Our unified image-text generation framework starts by obtaining text embeddings from the output of a T5 encoder on the raw text. Similarly, raw images are processed through a pre-trained VQ tokenizer to produce image tokens. These image tokens are then embedded and combined with the T5 text features as input to the image-text encoder. Modality-specific decoders then work on the encoded image text features to generate either text or image tokens. The text decoder operates in an autoregressive manner, while the image decoder works in parallel. Both the encoder and decoders are based on transformer layers. For image-to-text, I2T, training, we input masked image tokens along with empty text embedding to the image-text encoder. We then use the features generated by the image-text encoder, as well as the ground truth text tokens prepended with a begin of sentence, BOSS, token as the input to our text decoder. We train the encoder and decoder using an autoregressive language modeling loss, which is a cross-entropy loss with label smoothing of 0.1. For text-to-image, T2I, training, we use masked image modeling for image generation. The training objective is to reconstruct masked image tokens based on the unmasked image tokens and the paired text features. We use a cross-entropy loss between the ground truth 1 hot image tokens and the output of the image decoder. Our cycle consistency training paradigm allows training with image-only and text-only data. The key idea is to first create the corresponding text image from the image-only or text-only data, and then use the created data as input to reconstruct the original image, text. This allows us to apply cycle consistency supervision on image-only and text-only data. In the text-image-text, T2I2T, cycle, we first create pseudo-paired image tokens for input text using our T2I inference pipeline. We then apply a random mask to these tokens, perform reconstruction on them with the text using the T2I pipeline, and obtain the reconstructed synthesized image. Finally, we randomly mask this image and use it to generate text using the I2T pipeline. The objective of our cycle paradigm is to enforce consistency between this generated text and the original text. In the image-text-image, I2T2I, cycle, we first create pseudo-paired text tokens for input image tokens using our I2T inference pipeline. We then use the I2T training pipeline to predict new text tokens from the previous ones and the masked image tokens. We then mask the image, and pass it through the T2I pipeline with the predicted text to reconstruct the masked image tokens. The loss enforces consistency between the reconstructed and the original image tokens using cross-entropy. One challenge in our cycle training is that the predicted image and text tokens, which are not differentiable. To solve this, we use a straight-through estimation on the predicted logits to approximate the gradient. We found that this approach helps improve both text-to-image and image-to-text performance. Section Summary. The ITIT framework is a generative vision language training method that can be applied to unpaired image-only and text-only data. It uses a unified image-text encoder and separate image and text decoders to enable text-to-image and image-to-text generation. The framework incorporates cyclic losses to ensure consistency between the generated text and images, allowing for training with image-only and text-only data. Section: Results. In our study, we used 3 datasets: CC3M, WebLI, and Shutterstock. CC3M has 3.3 million high-quality image-text pairs. WebLI, with 111 million images, is noisier and results in poorer performance for image-to-text (ITIT) tasks. Shutterstock, with 398 million images, is labeled by human annotators, which is a costly and time-consuming process. For most of our experiments, we used CC3M as our paired dataset, half of the WebLI images as our unpaired image dataset, and the remaining half of WebLI texts as our unpaired text dataset. This split ensures that corresponding image-text pairs are not present in our unpaired image and text splits. We used the Shutterstock dataset to analyze how image-text ITIT scales with different numbers of paired and unpaired data samples. We set the input image resolution at 256 by 256 pixels, consistent with previous studies. After processing through the VQGAN tokenizer, the image token sequence length is 256 tokens. The raw text, with a maximum length of 64, is tokenized and embedded using a pre-trained T5 encoder. These embeddings are then combined with the image token embeddings as the input to our image text encoder. We experimented with different sizes of transformers for our image text encoder. For training, we used Adafactor to train the model for 1.5 million steps with a batch size of 2048. We used a cosine learning rate schedule with a warm-up of 5,000 steps and a maximum learning rate of 0.0001. For other experiments, we followed the same training approach but trained the models for 500,000 steps. We evaluated our model using the commonly used MS-COCO benchmark and evaluation protocols. For image captioning, we evaluated both the zero-shot and fine-tuning performance of ITIT on the COCO-Carpathy split and reported the CIDR score. For text-to-image generation, we evaluated ITIT on 30,000 image text pairs randomly selected from the COCO Captions training set and reported the Frechet Inception Distance (FID) score. We also evaluated ITIT's performance with different amounts of paired and unpaired data on the Shutterstock dataset. We found that more paired data improves both settings, but training with unpaired data significantly improves ITIT's performance over the baseline on both image captioning and text-to-image generation. Remarkably, with only 4 million paired data and 398 million unpaired data, ITIT achieves a similar performance as training with 398 million paired data. We also evaluated how ITIT's performance scales with the total amount of data used. We found that performance scales up with additional paired data. Surprisingly, however, additional unpaired data exhibits similar scalability as paired. In fact, we can achieve competitive results with only 1.2 million paired and 396.8 million unpaired examples, which is very competitive with using 398 million paired examples only. Finally, we evaluated our method in a more realistic setting, where the small-scale paired dataset can contain high-quality image-text pairs but a large-scale paired dataset has much lower quality. We found that our method is robust to low data quality in large datasets, and can in fact be used to achieve significantly better performance in settings when paired data is present but of low quality. Section Summary. The authors use 3 datasets: CC3M, WebLI, and Shutterstock, with CC3M being the highest quality dataset and Shutterstock being the most expensive to label. They train their model using a combination of image and text embeddings, experimenting with different transformer sizes. They evaluate their model using standard benchmarks and protocols. They also demonstrate that training with unpaired data significantly improves the model's performance, even achieving similar results with 100 times fewer image-text pairs. Additionally, they show that their method is robust to low-quality data and can improve performance in settings where paired data is of low quality. Section: Comparison to prior work. Let's compare our work with previous studies. In our comparison table, we've put our model, ITIT, side by side with the best image-to-text and text-to-image models using the widely accepted MS-COCO benchmark. What's interesting is that all the top-performing methods heavily depend on a large amount of paired image-text data for training. In contrast, our ITIT model is trained with only 3 million paired examples and an additional 55 million unpaired image and text examples. Despite this, our model outperforms many others that were trained on significantly more data for text-to-image generation. For image-to-text tasks, our model surpasses those using a similar amount of data and competes well with other top-performing methods. We also noticed that the type and size of the pre-training data can affect the CIDR score, a measure of caption quality. For instance, the GIT model, when trained from scratch with 10 million image text pairs, only achieves a CIDR score of 89.0. This is far from its reported performance of 144.8 when trained with 800 million image text pairs. We believe that increasing the size and diversity of the data could further improve our model's performance. We'll explore this in future work. Next, we examined the effectiveness of the four components of our ITIT model: T2I, text-to-image; I2T, image-to-text; T2I2T, text-to-image-to-text; and I2T2I, image-to-text-to-image. We found that combining T2I and I2T training in our model already improves image captioning performance. This is likely because the T2I training helps to prevent overfitting in I2T training. We also found that combining different types of data improves text-to-image generation but can negatively affect image captioning performance. This is due to the lower quality of image-text pairing in some datasets compared to others. We also tested some simple baselines for using unpaired image or text data during training. For example, we can perform text-to-text training without using images, or image-to-image training without using text. These baselines do improve performance over not using any paired data. We also tested a version where only half of the cycle is trained. This approach outperforms the non-cycle baselines. Finally, we tested the full cycle ITIT training. While T2I2T favors image captioning and I2T2I favors text-to-image generation, both significantly improve performance in both tasks. We also found that combining these two cycle losses can further improve performance. Interestingly, the full cycle loss outperforms the half-cycle baselines, showing the effectiveness of the gradient estimation step. We also found that the cycle consistency loss can slightly improve performance even without any additional data, likely because it encourages better alignment between images and text. However, the major improvements in both text-to-image and image-to-text generation mainly come from the use of additional unpaired data. With our ITIT model, we can easily perform cycle generation. The cycle generation often keeps the same semantics as the input text prompt. Without the cycle consistency training, the cycle generation misses some semantics after the first cycle. This shows that our cycle consistency training not only allows us to use unpaired image and text data in training, but also improves alignment between images and text for both image-to-text and text-to-image generation. In conclusion, we've proposed ITIT, a new training scheme that incorporates unpaired images and text into generative vision language training for the first time. Through extensive testing, we've shown that both the T2I2T cycle and I2T2I cycle effectively improve text-to-image and image-to-text generation performance. As a result, ITIT achieves competitive performance with state-of-the-art models, but with only 3 million paired image text samples. Our method can be used even when paired image text data is present, and is especially helpful when the pairing quality is low. In the future, we plan to scale ITIT to larger unpaired image and text data and model sizes, and to use more diverse datasets.